In 1995, a highly classified contract was signed between the Chinese government and the Russian helicopter design bureau Kamov, operating under absolute secrecy and strict non-disclosure agreements. The Russians were not hired to sell an existing aircraft, but rather to draft the foundational blueprints for what would become China's first dedicated modern attack helicopter, internally designated as Project 941. For nearly 2 decades, the global defense community believed the striking, angular Z-10 attack chopper was a purely indigenous Chinese triumph of reverse engineering and domestic innovation. It was not until 2015 that Kamov's chief designer publicly revealed that the aerodynamic layout, rotor dynamics, and structural architecture of the People's Liberation Army's premier tank hunter were actually born on Russian drafting tables. This secret arrangement allowed Beijing to bypass decades of dangerous trial and error in rotary wing combat design, buying a brilliant mechanical shortcut to a world-class airframe. During the late Cold War and through the early 1990s, the People's Liberation Army Ground Force recognized a glaring, almost fatal vulnerability in their tactical doctrine, specifically their complete lack of a dedicated attack helicopter. While the United States military was fielding the devastatingly effective AH-64 Apache and the Soviets were deploying their heavily armored Mi-24 Hinds, Chinese frontline forces were attempting to strap crude anti-tank missiles onto licensed copies of the civilian French Aerospatiale Dauphin, which they designated the Z-9. These militarized civilian utility helicopters lacked the structural survivability, the raw agility, and the deep sensor integration required to survive over a modern, radar-saturated battlefield. The Chinese military desperately needed an aircraft that could fly low, utilize terrain masking to avoid detection, pop up to fire-guided anti-tank missiles, and survive heavy small arms fire from entrenched ground troops. They required a complex machine capable of blunting armored spearheads, but their domestic aviation industry had precisely zero institutional experience in designing the complex flight dynamics of a tandem-seat, narrow-profile combat helicopter. Designing a machine where the pilot and gunner sit in a narrow inline configuration shifts the center of gravity drastically, altering how the entire airframe responds to aerodynamic stress during violent maneuvers. Kamov delivered the completed blueprints, extensive wind tunnel test data, and structural layouts before quietly walking away, leaving the Chinese engineers with the daunting task of actually building the machine and filling it with avionics, weapons, and most importantly, engines. It was exactly at this intersection of imported Russian structural design and domestic Chinese systems integration that the massive gunship project encountered its first near-fatal crisis. If detailed technical breakdowns of aviation design and strategy interest you, subscribe. I have got more of these coming. Interestingly, when Kamov drafted the Project 941 blueprints, they intentionally avoided using their signature coaxial rotor system, which stacks 2 sets of main rotor blades on top of each other to eliminate the need for a tail rotor. Instead, the Russian engineers drew up a highly conventional Western-style layout, featuring a 5-blade main rotor and a standard tail rotor, primarily to keep the overall weight low and the mechanical complexity manageable for Chinese manufacturers. Coaxial systems offer incredible lift and crosswind stability, but they require incredibly complex, heavy gearboxes that the Chinese domestic industry was simply not equipped to manufacture or maintain at a large scale in the late 1990s. The conventional layout provided a narrow, stealthy frontal cross-section, ensuring that the aircraft presented the smallest possible visual and radar target when flying directly toward an enemy anti-aircraft battery. The final blueprint called for a machine in the roughly 6,000 kilogram weight class, deliberately designing it to be lighter and more nimble than traditional flying tanks like the Russian Mi-28 Havoc. However, the central engineering nightmare for any helicopter development program is the propulsion system, And for the Z-10, this specific challenge almost killed the aircraft before it ever saw frontline service. The original Russian blueprints were heavily optimized around a specific power-to-weight ratio, demanding that the final aircraft be powered by engines producing at least 1,500 shaft horsepower each. Because domestic Chinese engine manufacturing was lagging decades behind the West, procurement officers opted to import the Pratt & Whitney Canada PT6C turboshaft engines to power their early prototypes. These Canadian power plants were historically reliable, highly fuel-efficient, and delivered exactly the raw mechanical force required to make the heavy airframe dance through the sky with maximum weapons payloads and thick armor plating. For the first few prototype test flights, the helicopter performed beautifully, perfectly validating both the Russian aerodynamic design and the robust Canadian mechanical muscle. But this imported power came with a massive geopolitical vulnerability that suddenly shattered the entire development timeline and sent Chinese engineers spiraling into panic mode. In 2006, under immense pressure from the United States government, Pratt & Whitney Canada was investigated and ultimately fined tens of millions of dollars for violating export controls. The investigation revealed that the engine software, specifically the full authority digital engine control systems, were being utilized in a heavily armed combat platform rather than the civilian utility helicopters they were legally approved for. The supply of Canadian engines was immediately and permanently cut off, leaving the Chinese aviation industry with a beautifully designed attack helicopter that suddenly had no heart and no means of propulsion. Forced into a corner with production deadlines looming, engineers had to hastily integrate the domestically produced WZ-9 turboshaft engine to keep the program alive. This forced domestic engine swap completely destroyed the carefully calculated power-to-weight ratio that the Kamov engineers had based their entire aerodynamic blueprint upon. The WZ-9 power plant struggled to consistently produce 1,000 shaft horsepower, representing a devastating loss of nearly 35% of the aircraft's intended propulsion force. To understand the severe operational consequence of losing 500 shaft horsepower per engine, one must look at the brutal physics of rotary wing flight, where every single kilogram of weight demands a specific, non-negotiable amount of lift from the spinning rotor blades. With the underpowered WZ-9 engines installed, the prototypes could barely lift themselves off the runway with a full combat load, let alone perform the violent evasive maneuvers required to dodge incoming surface-to-air missiles. The engineering team was forced into a desperate, aggressive weight reduction program, systematically tearing through the airframe to strip away anything that was not absolutely essential for basic flight and weapon delivery. The primary casualty of this severe aerodynamic crash diet was the heavy composite armor plating that was originally intended to protect the pilots and critical mechanical linkages from heavy machine gun fire. They reduced the armor coverage to the absolute bare minimum, relying heavily on lightweight graphene materials that could reliably stop a standard rifle bullet but offered highly questionable protection against heavier 12.7 mm anti-aircraft artillery. Furthermore, the payload capacity had to be drastically slashed to keep the aircraft from falling out of the sky during high temperature or high altitude operations, severely limiting its overall combat effectiveness. Instead of carrying 16 heavy anti-tank missiles like the American AH-64 Apache, the early production blocks of the Z-10 were often heavily restricted to carrying just 8 guided missiles. Every engineering choice became a brutal, unforgiving compromise between keeping the aircraft light enough to fly safely and keeping it heavily armed enough to actually matter in a mechanized firefight. Despite these severe physical limitations forced upon the airframe, the Chinese engineers poured massive state resources into ensuring the avionics and sensory equipment were cutting edge. They desperately attempted to offset the physical fragility of the lightened airframe with superior situational awareness, ensuring the pilots could see and strike the enemy before taking return fire. The angular nose of the Z-10 houses a sophisticated electro-optical suite featuring high-definition forward-looking infrared cameras, precision laser rangefinders, and daylight television sensors designed to peer through battlefield smoke and adverse weather conditions. This sensor turret is seamlessly integrated directly with the pilot's helmet-mounted display, utilizing a digital tracking system that monitors the exact orientation of the crew's heads. By slaving the chin-mounted 23mm chain gun to this helmet tracker, the gunner can aim and fire the weapon at off-axis targets simply by turning his head and looking at the threat. The choice of a 23mm chain gun rather than a heavier 30mm cannon is a direct reflection of the aircraft's relentless battle against weight and recoil forces. A larger caliber weapon provides superior armor-piercing capability, but the massive recoil impulse from a 30mm gun firing at high cyclic rates can cause severe harmonic vibrations throughout a lightweight helicopter structure. By stepping down to the slightly smaller 23mm round, engineers saved critical hundreds of kilograms in weapon mass, ammunition storage weight, and structural reinforcement plating. This specific capability mimics the famous weapon slaving system of the American platforms, significantly reducing the required engagement time during chaotic, low-altitude close air support missions. By giving the gunner the ability to look and shoot simultaneously, the design maximizes the fleeting, split-second windows of opportunity inherent to modern low-altitude helicopter combat. To strike enemy main battle tanks from well beyond visual gun range, the aircraft was deeply integrated with the AKD-10 air-to-surface missile. This advanced weapon system was specifically designed to mirror the flight profile, range, and destructive armor-piercing capability of the legendary American AGM-114 Hellfire missile. Knowing what you now know about its early engine struggles and forced armor compromises, do you think the design approach was worth the tactical trade-offs? Share your thoughts below. The AKD-10 utilizes semi-active laser homing technology, meaning the helicopter's front seat gunner or a forward infantry observer must paint the enemy tank with a highly concentrated coated laser beam. The missile rides that reflected laser energy directly through the top armor of the target, executing a high arcing trajectory before plunging downward at supersonic speeds to ensure maximum lethality upon impact. However, the strict operational requirement to maintain a constant laser lock on the target leaves the helicopter dangerously exposed during the entire time of the missile's flight. The pilot is forced to hover in place or fly in highly predictable, shallow patterns while the missile travels to its destination, completely negating the helicopter's natural agility. This operational requirement directly clashed with the aircraft's intentionally reduced armor protection, making it highly susceptible to enemy anti-aircraft fire during the final critical seconds of a missile engagement. To defend itself from enemy aircraft while exposed, the Z-10 is also uniquely equipped to carry the TY-90 air-to-air missile, a weapon expressly purpose-built for helicopter dogfighting. Unlike traditional shoulder-fired missiles adapted for helicopters, the TY-90 features a specialized infrared seeker and a laser proximity fuse designed to specifically target the main rotor mast of enemy helicopters, guaranteeing a catastrophic kill. The severe physical limitations of the early underpowered models became painfully obvious when the People's Liberation Army Ground Force attempted to deploy the aircraft to the extreme high-altitude environments of the Tibetan Plateau. In aviation physics, altitude is directly correlated with air density, and helicopter rotors absolutely require dense air to grab onto to generate upward lift. When flying at elevations exceeding 12,000 feet, combined with hot summer temperatures, the resulting high-density altitude rendered the early generation Z-10 nearly useless in the mountainous border regions. The thin mountain air robbed the domestic WZ-9 engines of even more power, making safe flight operations incredibly hazardous and terrifying for the flight crews. The military was frequently forced to operate them with half-empty fuel tanks, stripped ammunition loads, and no external rocket pods, just to maintain a safe hover out of ground effect over the jagged terrain. This severe high-altitude performance deficit was broadcast to the entire international defense community during the rigorous export market evaluations when the Z-10 was aggressively pitched to the Pakistani military. Pakistan requires its combat helicopters to operate dynamically in the grueling high-altitude ranges of the Himalayas, where brutal crosswinds, sudden downdrafts, and freezing temperatures test the absolute limits of rotary wing aerodynamics. During extensive field trials in 2015, the Chinese helicopter simply lacked the reserve engine power to safely maneuver through the treacherous mountain passes while carrying a full combat load. Consequently, Pakistan initially chose the Turkish T-129 Atak helicopter, a slightly smaller but brilliantly optimized machine with highly robust engines that handled the high-altitude demands without breaking a sweat. This rejection was a massive commercial embarrassment for the Chinese defense export industry, serving as a harsh, unignorable public validation of the compromises forced upon the airframe by the original engine embargo. The harsh, undeniable lessons learned in the mountains forced a massive, accelerated national engineering program to finally resolve the propulsion crisis once and for all. This relentless push led to the successful development of the Z-10 turboshaft engine, heavily co-developed with extensive engineering assistance from the French aerospace company Safran. This new domestic power plant finally delivered the 1,500 shaft horsepower that the original Russian Kamov blueprints had demanded nearly 2 decades prior, completely transforming the aircraft. With the installation of the Z-10, the aircraft was essentially reborn, instantly reclaiming its intended heavy payload capacity, rapid climb rate, and overall violent agility. Engineers were finally able to reinstall the heavy composite armor packages around the tandem cockpit and the engine nacelles, significantly upgrading the survivability of the crew against ground fire. With the weight restrictions finally lifted by the new engines, later modernization efforts introduced advanced millimeter-wave radar systems, prominently mounted in a small dome-like radome directly above the main rotor mast. This over-the-mast radar installation represents a massive leap in tactical survivability, allowing the helicopter to remain completely hidden behind trees, buildings, or mountain ridgelines while the radar physically peeks over the obstacle. Once the spinning radar identifies an armored column, it rapidly feeds the precise targeting data to the primary flight computer, allowing the crew to process threats in total safety. The helicopter can then launch active radar homing fire-and-forget missiles without ever exposing its main body or its spinning tail rotor to enemy visual sight lines. This critical upgrade fundamentally shifted the platform from a reactive, vulnerable close air support platform into a proactive, highly stealthy hunter-killer capable of managing multiple engagements simultaneously. Furthermore, as the engine power increased, the exhaust nozzles were aggressively redesigned and entirely rerouted to enhance the aircraft's defense against modern heat-seeking weapons. The exhaust pipes were turned to point upward, directly into the massive downward airflow generated by the main spinning rotor wash. This specific architectural choice instantly cools and widely disperses the hot exhaust gases, severely degrading the thermal signature of the helicopter and drastically reducing the lock-on range of enemy man-portable air defense systems. Additionally, the entire tail boom structure was heavily reinforced in the latest production blocks to prevent the severe harmonic vibrations that plagued the early models during rapid deceleration maneuvers. Every single operational flaw discovered during the initial compromised production run was methodically analyzed, re-engineered, and subsequently patched in the newer iterations actively rolling off the assembly lines. When directly compared to the heavily proven American AH-64 Apache, the fully realized Z-10 presents a fascinating contrast in modern attack helicopter combat philosophy. The Apache operates essentially as a flying fortress, explicitly designed to absorb incredible amounts of battle damage, haul 16 heavy missiles, and dominate the battle space through sheer technological superiority and overwhelming, punishing firepower. However, all of that heavy depleted uranium armor, excess ammunition, and heavy sensor equipment makes the Apache incredibly heavy, limiting its raw acrobatic agility and making it a somewhat predictable, slow-moving target in a visual dogfight. The Chinese machine, even with its upgraded engines and restored armor packages, remains noticeably lighter and visibly more maneuverable on a kinetic level. It is highly capable of executing violent banking turns, rapid pitch changes, and sudden altitude drops that would severely stress the structural limits of a fully loaded American platform. Another highly relevant comparison in the global rotary wing market is the European Eurocopter Tiger, which shares a remarkably similar visual profile, design philosophy, and weight class with the Chinese aircraft. Both of these advanced helicopters prioritize a narrow frontal cross-section to deliberately minimize their visual profile and radar signatures when flying aggressively toward an enemy anti-aircraft position. The tandem cockpit seating arrangement places the weapons officer in the front seat and the pilot in the rear seat, raised slightly to provide clear, unobstructed forward visibility over the gunner's helmet. Both the European Tiger and the Z-10 suffered deeply from early underpowered engine woes, and both ultimately rely heavily on advanced electronic warfare suites, laser warning receivers, and automated flare dispensers to survive. However, while the European Tiger program has suffered from notoriously low readiness rates and complex, expensive maintenance requirements, the Chinese military has aggressively mass-produced their helicopter to ensure total numerical supremacy. Operating the Z-10 in a high-intensity, modern conflict against a heavily armed peer adversary would require an immense amount of tactical discipline and bravery from the flight crews. Because the absolute armor protection still trails slightly behind the heaviest Russian flying tanks and American platforms, Chinese pilots are strictly trained to rely exclusively on nap-of-the-earth flying. This incredibly dangerous technique requires the pilot to stay mere feet above the treetops and terrain features, actively using the physical geography of the battlefield to remain permanently below the enemy radar horizon. Their tactical doctrine heavily emphasizes using encrypted data-linked communications to coordinate massive, multi-ship ambushes, where one hidden helicopter acts as an unseen spotter while others launch their missiles from behind solid cover. This heavy reliance on network-centric warfare effectively means the helicopter acts less like an independent lone wolf and more like a highly mobile, lethal node in a much larger integrated digital kill web. From a strict maintenance and logistical perspective, the agonizing shift to entirely domestic engines, radar systems, and avionics has provided the Chinese military with a completely sovereign supply chain. This total independence completely immunizes the entire attack helicopter fleet against any future Western diplomatic sanctions or sudden parts embargoes during a major regional conflict. Frontline ground crews consistently report that the diagnostic systems built into the airframe are highly intuitive, utilizing digital fault isolation modules that significantly reduce the required turnaround time between intense combat sorties. The main rotor blades themselves are constructed from highly advanced composite materials deliberately designed to withstand multiple direct hits from small arms fire without suffering catastrophic delamination or structural failure. This specific composite resilience theoretically grants the pilot enough precious time to maintain control of the spinning aircraft and safely limp back to a friendly forward operating base. The legacy of the Z-10 is a profound testament to the brutal, unforgiving nature of military aviation procurement, where a single broken link in a global supply chain can set a program back by an entire decade. What originally began as a covert Russian design exercise was nearly destroyed by a Canadian engine scandal, only to be painfully and slowly salvaged through years of domestic engineering triage and heavy operational compromise. It is incredibly easy to look back at the early production models, struggling to maintain altitude in the Tibetan mountains with half-empty missile racks, and mock the aircraft as a dismal failure of reverse engineering. But such a shallow dismissal completely ignores the staggering speed and efficiency at which the Chinese aviation industry systematically learned from those failures, iterating and improving the design until it finally matched its original lethal potential. Today, the heavily upgraded and heavily armed variants are actively patrolling the Taiwan Strait and the contested borders of the Himalayas, presenting a highly capable, combat-ready threat. Ultimately, the aircraft represents the exact historical moment the People's Liberation Army Ground Force stepped permanently out of the shadow of licensed civilian utility helicopters and entered the modern, highly lethal era of rotary wing combat. It is certainly not an invincible machine, and it still lacks the multi-decade, battle-hardened combat pedigree that makes the AH-64 Apache the undisputed, proven king of the attack helicopter world. However, it perfectly fulfills the exact strategic requirements of its domestic operators, providing a highly mobile, deeply integrated tank killer that can operate entirely free of foreign logistical interference. The aircraft stands as a permanent mechanical reminder that while quietly buying a Russian blueprint might give you a brilliant head start, mastering the dark art of the attack helicopter requires enduring the painful crucible of actual systems engineering. If you found this analysis useful, a like helps more people discover these deep dives.